Yes, Vijay. So shall we wait for a few more minutes or should I start the lecture? Because only I could see only 19 people. So if it is okay, then I'll start the lecture. Yeah, sure. So very good afternoon to everyone. So I'm Karthik Rajsekhar, Assistant Professor in the Department of Mechanical Engineering. So my lecture would be on the topic finite element analysis using ANSYS. So just a minute, I'll share my screen. Yes. So is my screen visible? Yeah. So my lecture would be on finite element analysis using ANSYS. So before I start the lecture, I would like to thank the head of the department of automobile engineering, Dr. Sharma sir, for giving me this opportunity. So my topic would be on, as I said, finite element analysis using ANSYS. So can anyone say what is the abbreviation of ANSYS before going into the lecture? So I hope you have completed 3 days of lecture. So can anyone tell me the abbreviation of ANSYS? What is ANSYS basically? Anyone of the student or participant? So ANSYS is nothing but analysis of systems. So here FEA is nothing but finite element analysis, which uses the concept of finite element methods. So if we go by the definition of finite element methods, so finite element methods is nothing but a numerical technique which is used to find an approximate solution to the given problem. I'll repeat the definition again. Finite element methods is a numerical technique which is used to generate an approximate solution to the given problem. So before going to my next slide, so we'll discuss something about this approximation technique. So usually, in order to solve an engineering problem, there are 3 basic techniques. So the first technique which we are trying to understand is an analytical technique or an analytical approach. So where, say for example, if I take a cantilever beam, you all know how does a cantilever beam would look. So if that cantilever beam is subjected to a point load at one end, so in order to find out the deflection of that beam, we have a direct formula, right? So you can use that formula of deflection, which is WL power 4 by 8EI. So substitute the Young's modulus, moment of inertia, all these things you would be able to generate the result of your deflection. And so in the similar way, you can find out what is the stress. So using a direct formulas, you are trying to generate a result. So that is what we call it as an analytical method. So here, if you take analytical methods, any kind of a simple problem can be solved easily. So say for example, any kind of a truss or a beam or this kind of a problem, you can directly solve using analytical method. So next, say for example, if you have a complicated problem, say for example, if you take a complex of assemblies, so your automobile chassis, and again, along with that, if you have any kind of complex assemblies, so finding out the deflection, finding out the stresses using a normal traditional technique will become very difficult. So in order to solve these kind of difficult problems, we would be using an approach called finite element analysis. I hope why we are using this finite element analysis is clear for everyone. And the third kind of technique is an experimental approach, where in the experimental approach, you are practically trying to test and say for example, if I said beam, so that beam you are practically testing in the environment. You're trying to give some input parameters. So based on the input parameters, you are trying to expect some effect. So that will come under your experimental approach. So if you look into an engineering problem, basically, as I said, we have 3 methods. One is an analytical method, next is a numerical method, third is an experimental method. So our prime focus is on this numerical method. So as I said, what is analytical method? It's a classical method. So you'd be able to get a closed form solution. So closed form solution, you can call it as an exact solution. So it is applicable for a simple problems like cantilever beam or a simply supported beam and these kind of things. So as I said, if you look into the bottom figure, I have a complex crane structure. So in order to analyze this complex crane structure using the simple analytical method, it will become very difficult, right? So in order to overcome this problem, we would be going for this approach called numerical method. So as I said, it is an approximate technique because since we are calling this as an approximate technique, it indicates that we are trying to get a closer solution. Say for example, if analytical will give you the exact solution, nearer to that we are trying to generate a result. And again, the results cannot be believed blindly. So whatever you try to do in the software, don't expect that all the results which you are supposed to generate is correct. It will show certain results, but don't think that all the results are correct. So in order to validate this result, definitely you need to do some analytical methods or either your experimental methods. So if I go for my experimental method, say for example, the problem with experimental methods is that, say the same beam, you can do it experimentally and find out the result. Say for example, if I have a complicated structure, generating a prototype, again doing the experimentation, finding out the results. So if the results are not feasible, then again what you need to do, you need to repeat the experiment again and again. So some amount of cost is involved in this process. So that is the disadvantage whenever you go for this experimental method directly. So in order to bridge the gap between these two things, we would be going for numerical method. So where we might be using either finite element method, either you can go for boundary element method, or you can go for finite volume method, or you can go for finite difference method. So I won't discuss in brief regarding these three things. So our focus is on mainly the finite element analysis. So I'll just give you the basic idea of finite element methods in this given lecture. So as we go by the definition, as I said earlier, it's a numerical technique used to find out approximate solution for the given problem. So what does this FEA use basically? So this FEA will use your matrix algebra to solve any kind of a problem. Say for example, if you are trying to solve a problem for a complex geometry, so there you are trying to generate certain amount of polynomial equations. So the current systems which are available right now, solving those polynomial equations will become very difficult because the order of that high polynomial equations would be very high. So the computation time which takes place in order to solve the problem will also be high. So in order to overcome this problem, we would be going, or we would be making a use of matrix algebra to solve this problem. So typical type of analysis you can do using finite element methods approach are structural mechanics. You can solve it. You can solve heat transfer problems, any kind of electromagnetics or a vibration problem. So any kind of things can be solved using your finite element analysis. So whenever we call a term finite element analysis, you might have seen in the previous lectures, there we'll come across a topic called discretization. So what does this discretization do? So in order to solve any problem, this discretization plays an important role in finite element analysis. So discretization is nothing but dividing a given system into known number of parts. So how many number of parts? As the name itself indicates, finite. So you are trying to divide a system into finite number of parts. So whenever you are trying to divide a system into finite number of parts, you will come across two things. One is elements and the other thing is node. So we'll understand what is this elements and what are these nodes. So if you look into this example, you have one object. So this is a continuous system. So this continuous system, you are trying to make it into number of elements. So you are trying to give number of divisions to the given system. Say for example, if I make it into 7 divisions, so this 7 division indirectly generates 7 elements. So even if you count over here, you have 1, this is 1 element, this is second element, third, fourth, fifth, sixth, and seventh. So whatever the object you have, whenever you say that you're trying to mesh your model, it indirectly indicates that you're trying to discretize the given system into known number of parts. So here I've discretized my given system into 7 parts. So I can see my 7 elements. And again, remember each element is surrounded by a node to one end, a node to the other end. So you can see the number of nodes over here. So each element, say for example, if I say I have 1 element, so 1 element has how many nodes? 2 nodes. So if I have 2 elements, then it has 3 nodes. So in the similar way, if you can look into this given figure, I have 5 nodes over here. So if I go for finite element method, so finite is nothing but reduces the degrees of freedom from infinite to finite. So what is this degrees of freedom? You know that degrees of freedom is nothing but the independent motions that an object can make in a three-dimensional space. Generally, if you say any object has finite degrees of freedom, we cannot say that it has finite degrees of freedom. Basically, any kind of object, if you take, it has infinite degrees of freedom. It can move to any other location. But for our convenience, we are trying to assume that it has only 6 degrees of freedom. So those degrees of freedom are 3 translations and 3 rotations. And next, E is nothing but element. So you have already seen that what are the results which we are trying to get. So those results is based on your elements itself. And as you increase the number of elements, you will be able to get a closer solution to your exact solution. If you have less number of elements, then what are the result which you are trying to generate, that would be far away from your analytical result. And next, if you go for a method, so we are using different methods, certain numerical methods to solve or to generate a numerical solution. So I hope this slide covers the basics of the discretization. So discretization is nothing but dividing the given structure into known number of parts, or dividing an object or any kind of system into known number of parts, then analyzing accordingly. So whenever you discretize a given system, it has elements and it has nodes. So if you can look into the bottom figure, so here you could see a bracket where this entire model is a meshed model. It has elements, and along with that elements, it has nodes. So if you give sizing for this entire geometry, you would be able to get a meshed model. So to this meshed model, you can see the element, and you can see the element connected by means of nodes, and again the corresponding loading conditions and boundary conditions. So any kind of a problem, if you want to solve using finite element analysis, these are the basic things which you need to do. So you need to mesh your model, you need to apply the boundary conditions, and along with the boundary conditions, you need to apply the load conditions. So as I said, the advantages in the earlier case, why we are going for this finite element analysis, you can see it. Reduction of design and development time, optimized product performance and cost, elimination on reduction of testing. So before going for directly testing, you can go for numerical analysis, validate your model, then you can go for testing. So unnecessarily, if you create a model or if you experiment it, and if your results are not within the limits, then again you need to start from the scratch. So that creates a problem. So for that reason, we would be going for your numerical technique. So what is the workflow process we have in finite element analysis? So you can see a flow chart here, which indicates your workflow process. So you have inputs. So that inputs may be of material or drawings. We have a geometry preparation. So in order to prepare a geometry, there are 2 ways to prepare a geometry. Either you can model the geometry in your ANSYS software, or else you can use CAD software, which might be of SolidWorks or a CATIA or any other software. Then convert it into a suitable file format, then import it to your ANSYS workbench or an ANSYS mechanical, then solve the problem. And next is your analysis step. So what kind of analysis you can perform in this ANSYS? Either you can go for static analysis. So along with static analysis, we can also go for thermal analysis or a dynamic analysis, which might be a modal analysis or a transient response analysis. So any kind of analysis can be carried out. It depends upon your actual model which you want to analyze, whether you want to analyze any kind of a static model or a simple you're trying to generate a stresses or deformation, or if you want to go for finding out the frequencies of the given system, you can go for modal analysis. And again, the important step is your discretization. So how many divisions you want to make, how many elements you want to generate, all these things would come under your discretization. Next, again, your loading conditions. So what kind of loading you want to give, whether you want to apply a uniformly distributed load, or you want to apply a point load, or you want to apply uniform varying load, or if you want to go for a thermal problem, there the loading is nothing but your temperature. So if you want to give a temperature, so all these things will come under your loading condition. So once you discretize, you need to give the loading condition. Along with the loading condition, you need to give one more thing called boundary condition. So any object in a real world environment, so you need to constrain that model in certain directions. So since we have spoken about this degrees of freedom, we have 6 degrees of freedom, 3 translations and 3 rotations. So if you take an example of a simple cantilever beam as we discussed earlier, so you know that one side of the cantilever is fixed in all degrees of freedom. So the translations along the 3 directions, which is along x, y and z, and the rotations along the 3 directions, which is x, y, z. So all these things should be fixed accordingly. So that will become your boundary condition. Next, you need to go for solution, where you need to give certain amount of analysis settings. What are the outputs you want to generate? You need to give it, solve it, then generate the result. So what is your result? You would be able to get a stress or a strain or a deformation or whatever it might be. What are the field of interest you want to analyze? You can give accordingly and you can generate a result. And again, you need to validate this result. So as I said, you would be able to generate one solution or one result in ANSYS. So that result, you cannot directly say that it is the correct result. So you need to validate that result by means of any kind of analytical method or an experimental method. You can do it, validate, then compare both the things. Then only you can say that the result which is obtained in ANSYS is correct. So don't think that whatever you model, whatever you do analysis, what are the result which you are trying to get is correct in all aspects. So you need to validate that result, then only you can say that your results are correct. And after validation, finally you would be able to generate a report. So this is the general workflow process which we have in ANSYS. So since I have spoken about the degrees of freedom, as I said, degrees of freedom is nothing but the number of independent motions that a body can make in a 3-dimensional space. So if we look into a 3-dimensional space, so say for example, I have one line element. So this line element is surrounded by 2 nodes. So since it is in 3-dimensional space, it has 3 translations along x, y, z and 3 rotations along theta x, theta y and theta z. Similarly, if I go for a 2-dimensional space of a line, I have, with respect to the coordinate system, I have translation along x, along y, along with that I have the rotation. And simply if you take a point, it has only the translations along x and y axis. So the number of degrees of freedom of the given structure will depend upon the type of element you take it. Whether you take a 1D element or whether you take a 2D element or whether you can take a 3D element. So since we have spoken about nodes and elements, you can see a plane figure over here which has infinite number of nodes. So you know that for each node, it has 6 degrees of freedom, which is 3 translations and 3 rotations. So total degrees of freedom available for the given figure or the each node, we have it as 6. So the total equations which are supposed to generate are nothing but number of nodes multiplied by degrees of freedom for each node. So infinite multiplied by 6, you'll be able to get some infinite number of equations. Now, if you can look into the same figure here, after discretization, you have generated the number of nodes. So here, this is my element 1, this is my element 2, this is 3, and this is my 4th element. So you can count the number of nodes. This is 1, 2, 3. So total, you have 9 number of nodes. So 9 number of nodes multiplied by number of degrees of freedom for each node is 6. So the total number of equations which you are supposed to generate is nothing but your 54 number of equations. So imagine solving this 54 equations using manually by using the traditional FEM approach will become very difficult. So that is the main reason we are using this software in order to generate the required result. So if you look into the type of elements which are used, so we have different types of elements. We have 1D element, 2D element and 3D element. So we have 1D element, 2D element and 3D element. So if I take an element shape as line, so we have a rod or a bar element or a beam element or a pipe element. So this is basically used for long shafts or a beam or a pin joint. So if you go for 1D element or a 2D or 3D, so if you go for 2D elements, so what are these 2D elements? So any kind of analysis if you want to do for sheet metal parts or an instrument panel or any kind of complex components, you would be going for a 2D element. And where 3D element are used, say for example, take your connecting rod, take your transmission casing, take your engine block. So in order to solve all those problems using your finite element analysis approach, then we need to go for a three-dimensional element. So in order to solve a simple problem like a beam or a bar or any kind of a truss problem, say for example, you would be going for a one-dimensional element. So the amount of the type of material which you are used also plays an important role whenever you are trying to solve a problem in finite element analysis. So not only these things, you have different types of other element types which are basically used in your other CAE softwares. So if you go for element types in ABAQUS, so you might have seen the previous lectures on ABAQUS. You can see that these are the different element types which are available. So we can have a shell element, we have a 4-noded continuum element. So these are some of the elements which are available. So if you are trying to solve a beam problem, say for example, you would be specifically going for this B31 element. In the similar way, if you go for ANSYS, here also we have different types of element. Either you have a linear element or a quadratic element. So depending upon the type of geometry, you need to select the element type accordingly. Say for example, if I'm trying to have, or if I want to do the analysis for, as I said, engine casing. So it's a three-dimensional solid. So for a three-dimensional solid, either I can go for solid 45 or solid 185. Along with these two things, you can also see an element order, which is quadratic. So here you can select solid 186 or solid 187. So as the element order increases from linear to quadratic, your accuracy of the result will also increases. So these are the different types of element types which are used for your analysis. So depending upon the type of analysis you do, you need to select your element type accordingly and try to solve it. If I take a one-dimensional element, say for example, solving that one-dimensional element using a 3D solid element type, it doesn't make any sense. But solving that beam problem by using this B31 element type, that does make a sense, because you are correlating the actual procedure or the actual behavior of your beam. So if I take a beam, say for example, it has at each node it has 2 degrees of freedom. One is a translation and the other is a rotation. This software ANSYS does not know that for a beam element it has translations and rotations. Until unless you mention it at some place, it does not know the exact behavior. So that behavior can be given in terms of an element type. So that is the reason whenever you solve any problem in ANSYS mechanical, this element type plays an important role while solving the problem. If you take an improper element type and try to solve it, that software will not solve the problem. So it definitely creates an error. So these are the different types of element types which are used in your CAE softwares. Now the next question which comes is how to decide this element type. So the selection of element type will depend upon 3 things. One is your type of analysis, one is your geometric size and shape, and other is your project time. So say for example, if I have a beam, the same thing which I have explained you earlier. So solving that beam problem using a solid element will take much amount of time rather than solving that beam problem using a beam element type. So it would take a less amount of time, and if you change the element type, in certain cases, the time taken to solve the problem will also increase. And also the type of analysis which you want to perform, whether you want to go for a static analysis, whether you go for a dynamic analysis, based on that also you would be able to select the corresponding element type. And also on your project time. So as you know that the time taken to solve the problem, if it is increases, then again the computation time would increase. Indirectly it would take your project time. So that is the reason you need to select an element type in a proper way, analyze the problem, take proper element type, solve it, get the unknown things known as stresses, deflection, or strains, or whatever. Now, since we have spoken about the meshing, so here meshing accuracy plays an important role. So if you take a simple area, a circle, so if I divide it into three elements, say for example, if I do the meshing, I could see a shape in terms of a triangle like this. But the same thing, if I want to divide it into number of elemental division, say for example 4, after meshing I could see the shape of the circle as square. So the same circle, if I made it into, again, say I'm trying to increase the number of divisions, now I have made it to 6. You can see the shape of an hexagon. Now I've made it into 8 divisions. So if you can see, if I made it into 8 divisions, I could closely approximate the shape of your circle while meshing. So if you increase the divisions or increase the mesh size, you would be able to get a proper mesh. So you'd be able to properly approximate the exact shape. So even if you take this T pipe, you can see it over here at the corner. So if I made it into 2 elements along the radius, you can see the mesh. The accuracy of mesh here is very poor. But if I increase the number of elements, you can see the accuracy of the mesh got increased. And further, if I make it into 8 divisions, you can see how proper your mesh is. So this meshing will play an important role while doing any kind of analysis. And wherever your field of interest to find out the stress or a deflection at that region, you need to make sure that the number of elements or the accuracy of the mesh should be more at that particular region. If the accuracy of that mesh is poor in that particular region, and again your results would go down. That's the reason meshing accuracy will play an important role whenever you take finite element analysis. So since we have spoken about finite element analysis, as I have already said that this finite element analysis which uses a concept of finite element methods. So in finite element methods, we have one characteristic equation. So in the earlier slide, I've told you one thing called, it uses an equation in terms of, or it generates an equation in terms of matrix algebra. So here, this characteristic equation will play an important role in your finite element analysis. So that equation is KQ equal to F, or you can call it as KD equal to F. So F is nothing but force, K is nothing but the stiffness, Q is nothing but the displacement, or D is nothing but your displacement. So K is nothing but the stiffness, which is the characteristic property of the element. F is nothing but the force. Say for example, the same beam if I have taken, I am applying a point load at one end. So that force is known. My unknown thing is nothing but my displacement, and K is nothing but the stiffness. So how to get this stiffness? In the sense, we have one matrix called stiffness matrix. So for each element, say for example, if you can count the number of elements here roughly, I'm taking this as 1, 2, 3, 4, and 5. For each element, it will try to generate one matrix called stiffness matrix. So for this region, it generates one K1 matrix. For this element, it will generate K2. Similarly, K3, K4, and K5. So this combined together, we'll be able to generate one matrix called a global stiffness matrix. So force acting on the given system is known. Stiffness matrix, you'd be able to generate from the number of elements which are available. Q or D is nothing but the unknown displacement which you need to find out. So in order to find out this unknown displacement, I can simply send this K onto the other side. This will become inverse. So K inverse of F will give you the displacement. So here you would be getting a matrix. Here you would be getting a matrix. Multiply those two things, you would be able to get the unknown thing called displacement. So any problem, if you take in finite element analysis, it uses this characteristic equation. So what is the first step? As I said, formulate the stiffness matrix. So this would be taken entirely by the software. Formulate the stiffness matrix, measure given model. Solving would be done by the software. Then find out the unknown displacements and stresses. So these are the basic step-by-step procedure which on the background of ANSYS it would take place in order to get the result. So if I take the FEA process flow, so we have pre-processing, we have solution, we have post-processing. So So pre-processing is nothing but defining your element type, right? Then meshing your model, applying the boundary conditions and the loading conditions. Everything will come under your pre-processing. Now coming to the solution. So what you are trying to do, you are trying to find out certain unknown things. So you are trying to solve the problem. You'll be giving certain amount of solution step. So after solving the problem, you will be able to generate a result. So that result is nothing but your stresses, strains, and any other result we are trying to generate using post-processing. So in finite element analysis, these are the basic steps we have: pre-processor, solution, and post-processing. Give the inputs, solve it, generate the output. So that is the basic flow process we have in finite element analysis. Now the next question which comes into our mind is, what kind of analysis can be done using a software? So you can do static analysis, you can go for dynamic vibration analysis, you have explicit dynamic analysis. So different types of analysis you can do it. So say for example, if you are trying to do a tensile test, right? You are trying to apply a displacement at a constant rate. So then you'd be going for quasi-static analysis. Say for example, if you go for dynamic analysis, you're trying to find out a natural frequencies of a given system, you'd be going for a dynamic analysis. In the similar way, you can also go for thermal analysis. Say if you want to predict your conduction, so if you give conduction to the given system, what is the output, then what is the temperatures which I'm trying to get. So all these things can also be done using different types of analysis. Now in today's session, so I would be focusing on one important thing called optimization. So we'll understand what is this optimization by means of one simple example. So if you go for optimization, say I'm trying to take the same example of a beam, right? So I'm trying to do the numerical analysis using FEM method. I'll try to generate the results for stress, displacements, and all. So after getting the result, so you have one thing called topology, which indicates your size and shape. If you take a disc brake of your automobile, say for example, the disc has certain amount of thickness. So if you solve static analysis, give some pressure inputs and generate a result, you can see certain regions where your stress is concentrated. So wherever your stress is concentrated, there you need to increase the thickness of your disc where that stresses can be reduced. And wherever the stresses are not acting, then at that region you can minimize your material, because any kind of automobile component which you take, important thing which you need to do is to minimize its weight. So in order to minimize its weight, you need to do certain hypothesis, certain optimization such that you'd be able to generate a result in such a way that it should have optimum weight. Along with that, it should have proper stress and proper deformation. So the main idea or main motive of optimization is that wherever you have higher amount of stress concentration or higher amount of stress, there you are trying to increase the thickness of that material such that your stress can be reduced. And wherever the region where the stress concentration is not that much, then there is a chance where you can reduce the amount of material so that you can compensate the weight accordingly. So for that reason, we would be going for the optimization in your finite element methods. So whenever we go for optimization using finite element methods, we have one thing called design of experiment. So what is this design of experiment? So before going for design of experiment, can anyone answer what is an experiment basically? Can anyone define what is an experiment? Any one of the participant can define what is an experiment? Am I audible for everyone? Can someone respond? Yeah. So can anyone say what is an experiment basically? Any participant? Okay, fine. So experiment is nothing but what? You're trying to give certain input to a given system. So whenever you give certain input to the system, it generates certain effect. That effect is nothing but your output. Say if I take a beam, so the beam has certain amount of parameters which you already know that you have given in terms of an input. So based on the inputs like your thickness, like your width and your length, all these things, you'll be able to generate certain amount of output. So the output might be your stresses, deformation or anything. In certain cases, say for example, you have designed a beam and you have thought of in such a way that my beam which I have designed should withstand a stress or should have a stress of, say for example, 45 megapascal. You don't know what thickness of the beam you need to keep in such a way that you'd be able to get that amount of stress. So in order to do these kind of manipulations and in order to design, in order to generate a perfect thickness to that particular beam such that it would be withstanding the stress limits which you have defined, we would be going for one thing called design of experiments. So what we do in this design of experiments, first we'll define a problem. So problem is nothing but, say for example, I'm trying to solve a simple beam problem. I'll define its objectives. I'll define the response and factors. I'll solve this. I'll analyze. I'll collect the data. Then I'll predict the results. Then again, if any additional experiments are required, I'll again try to perform that additional experiments. Then again, find out the corresponding result. So in order to do this design of experiments and all, I'll show you with a basic example using ANSYS. So if I open this ANSYS workbench, you might have seen this graphical user interface previously. So here on the left side, you can see different types of analysis which you can perform. So either you can go for a dynamic analysis, you can see model, you can go for a rigid dynamic analysis, you can go for a transient response analysis. So different types of dynamic analysis you can do it. And along with that, you can also go for a simple static structural analysis. So I'll go for static structural analysis. So if I double click on static structural analysis, so here onto the project schematic, you can see the analysis module. So here, as you have seen the steps which are there in finite element analysis. So first step is pre-processing, next is solution, next is post-processing. So all these things, your geometry, your modeling and all, these will come under your pre-processing. Solution, you are trying to solve it, results which you want to obtain. So whenever you are trying to do any kind of an analysis, right, first you need to set the type of material which you want to use. Say for example, my type of material is, say for example, I'm using a stainless steel as my material. So if I click on engineering data, if I double click it, so you can see in the database, you can see the default material which is available for solving a problem is a structural steel. So say for example, my material should not be of structural steel. It should be some cast iron or it should be of some other material. So you need to define your type of material which you are trying to use in analysis. So simply I'll do one thing, I'll suppress this and again I'll go for engineering data sources which is available at the top. So if you go for engineering data sources, you can see it on the top, you can see different types of materials which are available. So you have geomechanical materials, you have a composite materials, you have hyperelastic materials, you have a materials for additive manufacturing. Along with that, you have a general material. So if I double click on general material, further at the bottom, you can see different types of library of materials which are available. So you have gray cast iron, magnesium alloy. So these are the different types of materials which are available. Say for example, if I want to add a gray cast iron material, so I'll simply click on add. So what does it do? Whenever I go for an engineering project, so here by default, the material which it is supposed to take for analysis will become your gray cast iron. So in the similar way, you can go for different types of materials or the type of material which you want to analyze. So based on that, from the library of materials, you can take it. So or else you have one more option here where If I go for engineering data and if I click on edit, see, observe, I've recently added gray cast and iron as a material. So I'll suppress this. I'll activate again my structural steel. So by default, my material which I'm supposed to do for analysis will become my structural steel. So if you look into the bottom, you can see different types of properties which are available. So you already know that the Young's modulus of a steel is 210 gigapascal. You can see it 2 e power 11. And it also shows you the Poisson's ratio. Since it is an isotropic material, you have Young's modulus and Poisson's ratio accordingly. So along with these things, you have another option to add the material. So there are certain materials which are not there in the library. You can also add it. Say for example, I want to add an aluminum material. So I'll write aluminum. I'll select it. So after selecting as aluminum, you can come to the left side. You can see what kind of properties you want to give. I need to give two things. One is a modulus and other is a Poisson's ratio. So I'll go for isotropy. I'll select this. Here accordingly, I would be giving my Young's modulus and Poisson's ratio. So in this way, you can define your own material type. Whether it is a composite material, go for orthotropic elasticity. Where it is an anisotropic material, you can go for anisotropic elasticity. Correspondingly, you can give the modulus and Poisson's ratio to solve your problem. So if you don't want to add any kind of a material, you want to delete this. So simply select it, right click and delete it. And even this gray cast iron which is not required for you, right click over it and simply delete it. So in this way, you can add different types of material in your analysis. So not only in structural analysis, either if you can go for dynamic analysis or any type of analysis, you can add the material in this way. Now I'll go for project. So my engineering data, on the right side, you can see one tick mark. That tick mark indicates that your engineering data has been selected. Your material type is selected. Now I need to model my geometry. So in order to model my geometry, I'll simply go for geometry. I right click it. So here you can find two things which are graphical user interfaces, which is place claim geometry and other is design modeler geometry. So anything can be used in order to model your geometry. So I'll go for design modeler. I'll select it. So on the bottom, you can see that it is starting a design modeler. So within few seconds, it will show you how does your design modeler will look. So let it open. So whenever you are trying to solve any kind of problem in ANSYS, so the RAM and your graphic card and all these things also will come into picture, because since you are performing the computations, so if you have higher amount of RAM, it will try to compute it very quickly and try to generate the result. So since I have opened the design modeler, so this is how a design modeler will look. So here we have x-axis, we have y-axis, we have z-axis. So you can see different kind of planes which are available, XY, YZ and ZX plane. Say for example, I want to model something, some geometry in XY plane. I'll select my XY plane. So it shows my XY plane. I'll right click it and I'll click on look at. So it will show my XY plane. And also at the bottom, you can see the dimensions. So initially the units are in by default meters. So you can change this units. You can come into units. Instead of meters, you can change it to millimeter. So you can see that now here the units have been changed. Now on the XY plane, I'll try to model some geometry. So I'll go for sketching my geometry. Whenever I go for sketch, so you can see multiple number of options. Just like your AutoCAD and the SolidWorks software, you have multiple options to generate a model in the graphical user interface of ANSYS Workbench. Say for example, I want to generate a simple rectangle. I'll select a rectangle. So this blue point is nothing but my origin point. So I'll select it I'll simply place that rectangle like this. So after placing the rectangle, the next step is to give the dimensions for that. So in order to give the dimensions, here itself you find an option, dimensions. So what kind of dimensions? So whether you want to give horizontal dimension or whether you want to give vertical dimension or any other thing. So if it is in general, simply click on the line segment and place this somewhere on the screen. Simply click on the line segment, place it somewhere on the screen. You can see something called H1 and V2. So this H1 indicates your horizontal line distance, V2 indicates your vertical line distance. So horizontal line distance, it is showing that 53.104 mm. So now I'll make it as some 100. And vertical V2, it is showing as 34.24. Now I'll make it to some 50. So I'll use a scroll button to zoom in or to zoom out. So I can see one rectangle which I have drawn. Now this is simply a 2D sketch. Now I'll try to add certain amount of thickness to this, and I'll try to make it as a 3D sketch. So in order to do that, what I'll try to do is that on the top, you can see one thing called extrude. So extrude is nothing but you are adding certain amount of thickness to the given material. Along with that extrude, you can also go for revolve, you can also go for sweep, or you can also go for loft. So here I'll click on extrude. So if I click on extrude, it is asking you to select the geometry. So by default, the geometry would be selected. I'll simply click on apply. Now, what is the depth you want to give, or what is the depth you want to add to the given 2D sketch? Say for example, my depth I want to add, I'll call it as some 500 mm. So I'll write it as 500. So after making it as 500, you need to click on this generate. You can see a shape of thunderbolt. So here, if you click on generate and rotate it, you can see whatever the 2D sketch which I have drawn, a simple 2D sketch. For that 2D sketch, I have added certain amount of depth and I have made it as a 3-dimensional model. Now, since I'm trying to show you how does the design of experiments can be performed using finite element methods, so you have to define your input parameter. So my input parameter is nothing but my thickness. So I'll go for extrude. I'll select sketch. So if I select sketch, so what is the thickness? So this V2 indicates my thickness. So I'll select my parameter as thickness. So what I'm supposed to do over here, I'm trying to find out an optimum solution for a given problem in such a way that I would be giving a range of thickness stating from some 35 to some 65. So within this range, I'm trying to analyze it and I'm trying to find out a value of stress for the given problem. So I'll mention it as some thickness. I'll try to give this parameter, right? Now your modeling is completed. Now just minimize this. Since I've set a parameter called thickness, since I'm trying to do the design of experiments, you can see the parameter set over here, and onto the side of geometry, you can see a tick mark. It indicates that your geometry is fine. If there is any error in the geometry, it shows a cross symbol. So you need to modify or redesign your geometry. Now go for model, right click it, simply click on edit. So if you go for modeling, so it will show your model. Along with that, it will also show you the certain setup options. So what kind of boundary conditions and what kind of loading conditions which you want to give for the given system. So it takes some time to open this model. So we'll wait. So you can see here, whenever I open a model, that model is appeared over here. Now here, the next step is to mesh your model. So select mesh. So you have already seen in the earlier lectures how to give the sizing for mesh and all. So the same thing can be given for this, or else I can simply generate a default mesh. So right click on the mesh and simply click on generate mesh. So you can see your mesh model over here for the given a beam, whatever I have designed so far. So you can see the mesh model. So if you want to increase the number of element size, what you need to do, you need to go for sizing and accordingly give the element size. Then again, regenerate mesh, you'd be able to get it. Or else you've already seen how to give the face meshing. So you can select a face, do the same thing, repeat the step. You can also generate the mesh in that way. So your geometry is defined. So if I go for geometry, so my geometry is a solid. So if you go for solid, on the bottom, you can see the assignment of that material is nothing but my structural steel. In the way I have shown, where you have different types of materials added together, you can also change the material. But I have only one material so far, which is a structural steel. You can see the same thing over here. Now, in order to analyze this given beam, now I'll simply click on static structural analysis. I'll insert. So if you go for insert, you can see multiple number of options here. So you have loading conditions and also you have the boundary conditions. So first I'll try to apply the boundary condition, then I'll go for the loading condition. So I'm considering fixed support. So I am assuming that I'm trying to fix the one side of my beam, the number of elements or the face. I'll try to fix this in all degrees of freedom. So in order to fix this in all degrees of freedom, on the top, you can see either you can select a vertex, you can also simply select a vertex and lock it, or else you can select an edge, you can define this edge and you can make this edge as a fixed support, or else you can go for this face. Since I have to fix the complete face, I'll select this face. On the left side, I'll simply click on apply. So it indicates that the number of elements what I have over here, it is completely fixed in all degrees of freedom. Now my fixed condition is given. Now I need to apply the loading condition. So what kind of loading condition I want to give? Say for example, I want to give a point load, say for example. So I'll go for right click. I'll go for insert. Here, if you go for insert, you can find different things over here. So from this end, I want to apply a force. So I'll select a force. So what kind of force you want to apply? So whether the force is a vector component in the sense whether you want to apply a force in a particular direction or you want to apply a force in terms of a components. So here you can see the axis, x-axis, y-axis and z-axis. So along y component, if you want to apply a force, write down the value along the y component. If you want to apply a force along the x component, then again give certain value over here. So before doing that, I'll select my geometry. So simply I'll go for my edge. So my intention is to apply a point load at this given edge. So I'll select that edge, simply click on apply. Next, I'll apply a vertical component of force along y direction. Say for example, the force which I want to apply here is 5000. Since my force should act along the downward direction, so I'm trying to give that as minus 5000 and I'll simply click over here. You can see the arrow direction which is in terms of red, which indicates your y component of force of magnitude 5000 newtons. Right? So I have recalled the model. Then I have given the fixed boundary condition. Along with that, I have also given my point load. Now, my interest is to find out two things. I'll insert. I need to find out what is the deformation. So I'll simply click on solution. I'll right click it. I'll go for insert. I'll select deformation. I'll select a total deformation. So this is one of the output which I want to extract. And along with that, I'll go for insert. I'll go for stress. I'll select shear stress because my interest is to find out the shear stress also. So I'll select the shear stress. Along with that, I want to find out the safety factor. So I'll go for stress tool. I'll select equivalent 1 minus stress. So I've given these are my outputs. So based on the given inputs, I'm trying to find out the outputs, which are deformation, stress, and the safety factor. So simply now, since everything is off in terms of a green tick, it indicates everything is fine. You can directly go for solution, right click it, and simply click on solve. So what does this do? It will try to take the inputs which you have given for the system. So based on that, it will try to solve the problem. So it will try to build the mathematical model and try to generate your required results. So if you have seen in my earlier slides, I have shown you one characteristic equation, right? What is that equation? We have KD equal to something called F. So the same background manipulations and calculation would takes place in the software. So based on that, you would be able to generate a result. Now see, my result is completed. My solution is done. So if I want to look into the result of deformation, I'll simply click on deformation. So you can see if one end of that beam is fixed and onto the other side, if you apply a load, you got the deformation as how much? It is around 0.99 mm. In similar way, if you want to find out the stress, you can simply click on stress. You can see the value of stress is how much? 31.4. What are the units of that stress? The units of that stress is in megapascal. So it is around 31 megapascal. Since you are trying to solve, I am trying to assume this as a beam and solve it. You can see at the region of neutral axis, there is no stress which is going to occur. So these are the results which I have generated over here. Now, since, as I said, I'm trying to perform my design of experiments, here what I'll try to do is that my output parameters I need to give while solving the problem. Input parameters which I have given is thickness, which you have already seen in the earlier case. Here, my output parameters which I'm trying to give are nothing but my shear stress and also my safety factor. You can see the safety factor. The safety factor is around 4.2. So you can calculate the safety factor. So how factor of safety is calculated? You have one formula, allowable stress by working stress. So what is your allowable stress? Write it over there. What is the working stress? You'd be able to get from this analysis. So do this, you'd be able to get your factor of safety. So you got the factor of safety and shear stress. So these are the output parameters which I need to select. So I'll go for this maximum shear stress. I'll select this as my output parameter, and again I'll go for my safety factor, come to the bottom and select this as my output parameters. So the input parameters is the thickness which I have given. So what is the thickness I have given? I have given it around 50. Now my output parameters, I have taken it as what? Shear stress and factor of safety. So based on these two things, I'll try to do the design of experiments. I'll try to complete multiple number of iterations. Then I'll try to find out what is my optimum solution. So in this ANSYS, if you come to the bottom here, you can see one thing called design exploration. So here you can find one thing called response surface optimization. So this response surface optimization is basically used for the design of experiments. So as I've already told you what is your design of experiments. So I'll simply select it. I'll place it over here. So I'm trying to link my static structural analysis with my design of experiments. So I'll select design of experiments. I'll first click on edit. So if I click on edit, the first step which you can see is the input parameter, which is my thickness, and these are my output parameters, my shear stress, my safety factor. So if I select thickness, right, since I'm trying to perform a design of experiments, I need to give a lower bound and upper bound range of thickness. Say for example, my minimum thickness of the beam is 35 and my upper bound thickness I'm trying to give it as 65. So within this range of thickness, I'm asking it to find out what are the shear stress and what is the safety factor. So I'll give this lower bound and upper bound values and I'll simply click on update. So what does it do? It will try to do the design of experiment. So it will take a random thickness which is ranging from 35 to 65. So in between these two things, it will try to find out what is the shear stress and also it will try to find out what is the safety factor. So if you look into the thickness here, so I've given a thickness range of 35 to 65. So randomly it has taken multiple thickness over this end. So for thickness 50, which I've solved previously, I got the shear stress value as how much? 31.4 megapascal and factor of safety as how much? 4.2. Now, can anyone guess what will happen for a thickness of 35 mm? What happens to this stress value? So, can anyone guess what will happen over here?
Stress should increase.
Yeah, stress should increase, and what happens to this factor of safety? It will definitely decrease. So you can see for 35 mm thickness, so your stress value is how much? The maximum stress is 63.6 megapascal and the factor of safety got reduced to 2.08. So in similar way, it will try to find out for some random thickness ranging from 35 to 65. So let it do the iteration and find out the shear stress and the factor of safety. So if you go for the next thickness, see it is 65. So since it is 65, obviously the stress would reduce and obviously the safety factor will try to increase. So it takes some time to solve this problem, around 1 or 2 minutes. So it will show you for different thicknesses what are the shear stress and what is the factor of safety. I have taken a simple example of a beam to solve this. This approach, this design of experiments is applicable for any type of analysis, whether you want to do it for any wheel hub or any kind of chassis, automobile chassis, any kind of a thing. You can use this concept of design of experiment and you can find out the optimum result.
Excuse me, sir.
So you can see it over here. It is updating the design of experiment. So you can see for different range of thicknesses, right, which it has taken from, it has done some random iterations. So for that random iterations, it has shown you what is the stress value and what is the factor of safety. So if I go for a higher thickness, say for example 65 mm, you can see by default the stress will reduce, the safety factor would definitely increase. Now come back to your project. So I have done my design of experiments. Now I'll go for my response surface. So we'll understand what is this response surface. I'll right click on it. I'll click on edit. So here it does the number of iterations. It takes some 100 samples at the background, try to solve that iterations, and based on the given thickness range, between 35 to 65, what are the stress and what are the factor of safety which we have obtained earlier, that will try to show onto this table. So I'll just try to update the data. So it shows that it is updating the response surface. So if I go for this, since I have given the lower bound and upper bound value of thickness for the given beam, so it shows the stress and also the safety factors over here. Now come back to the project, I'll go for optimization. So select optimization and click on edit. Now whenever we go for a design of experiments, so we have one thing called objectives and the other thing is constraints. So I'll select this objectives and constraint. So here I need to select one parameter. So my parameter, my interest is to select two things. One is shear stress and the other thing is safety factor. So I'll select maximum shear stress over here. I'll select this maximum shear stress. I'll click on this type. I'll select seek target. So I don't know, in order to generate a stress value of, say for example 36 megapascal, I don't know what is the thickness of beam I need to give. So I'll keep a target here that my target is to achieve a stress value of 36 megapascal. So it is showing you my target is to achieve a stress value of how much? 36 megapascal. And one more thing which I want to give here is my factor of safety. I'll keep a target for my factor of safety, stating that my factor of safety should be at least 5. So I don't know what thickness of the beam I should give such that I would achieve this two targets, whether I can achieve this 36 megapascal or this factor of safety. So these are your output parameters. So you're trying to give this output parameters. So based on this output parameters, it will try to solve the problem and it will show you what kind of input parameter, which is nothing but thickness, you want to keep it so that you would achieve this 36 megapascal stress and again 5 as your factor of safety. So I have given my objectives and constraints. So I'll simply click on update. So if I simply click on update, it will try to do certain number of iterations on the backside such that for the given targets of 36 megapascal and given target of 5 factor of safety, what should be the optimum thickness I need to give for that beam. So I'll come to the bottom region. I'll select the candidate points. So if you can look into this result, it has given you my 3 optimum results. What are those 3 optimum results? So in order to achieve a target of my 36 megapascal and factor of safety, as you have seen, I have given the factor of safety there as 5. So in order to achieve closer result to my factor of safety and this stress, what is the thickness of the beam I need to give? So if I give a thickness of 48 mm, initially, if you can remember, I have given a thickness of how much? Can anyone remember what is the thickness I have given while modeling the geometry? I have given it as 50 mm. So in order to achieve my target, which is around 36 megapascal and factor of safety as 5. So taking these two targets into consideration, it has shown me that optimum thickness which I want to give for the beam as 48 mm. So in this way, in order to achieve your results, so you can do this design of experiments and all, do the analysis, give the input parameters, give the output parameters and achieve the optimum result. So in order to achieve my targets of 36 megapascal and minimum factor of safety as 5, I need to give the thickness of beam as how much? 48 mm. Imagine if you don't have this design of experiments concept, then what you need to do? For each thickness, starting from 35 to 65, you need to do each iteration. So for 35 mm, you need to model the geometry, solve it, get the result. Then again for 36, model the geometry, solve it, get the result. So it would take lot amount of time in order to solve the problem. So once you give your target values while solving the problem, you definitely get your optimum thickness which you can give in order to generate this target result. So this is a way you can perform a design of experiments. So I'm just trying to give you a basic idea of how to do the analysis using this finite element method. So this alone, whatever I have done up to results, would cover your basic static structural analysis. So this is the extra thing which I have told you, where in order to achieve an optimum result, how to give inputs to the design of experiments and how to solve it. I hope for everyone this concept is clear. So the same thing can also be applicable for any kind of geometry. Follow the same procedure, mesh it, analyze it, get the result. So this is what we do in the basic static structural analysis, and along with that we can also go for the design optimization. So this is one kind of optimization which you can do it. So the other type of optimization which you can do is that we have one more optimization called topology optimization. As I said earlier, topology indicates your size or your shape of your given geometry. So wherever you have large amount of stress, there if you increase the thickness, definitely the stresses would reduce. Wherever there is no stress at all, there you can remove certain amount of material, because adding more amount of material increases the weight of the component. Indirectly, it is not good for any kind of automobile component. So for that reason, you can also go for topology optimization. So I'll just explain you with the basic example how to do the topology optimization. So doing the topology optimization, what you have done in this initial analysis, the same technique you need to follow. So I'll go for simple static structural analysis. Okay. So before I go for static structural analysis, I'll do one thing. I'll just delete all those things. So I'll go for file, new. I don't want to save the existing ANSYS computed data. I'll simply select it as no. So it will open a fresh project schematic. So I've opened it. Again, I'll repeat the same thing. I'll go for static structural analysis. Now again, the material which I want to analyze, that I won't change it. If you want to change it, again, I've told you, right, what are the steps which you need to follow, that you can do it. And now I'll try to import my model in order to do the topology optimization. So you have seen it in the earlier case where I have modeled the geometry. So after modeling the geometry, what I have given, I have extruded it, then again performed certain computation, and I have generated the result. So that is one procedure. And the other procedure where you can get your geometry is by taking the geometry which you have done in any kind of a CAD software. Say for example, you have modeled some geometry using SolidWorks or using CATIA or any other software. So what you need to do, what are the modeling you have done in those software, you need to save it with certain data exchange format. So we have different types of data exchange format. We have initial graphic exchange specification, which we call it as IGES, and we have Parasolid, we have product data exchange specification. So we have different types of those specifications. So whenever you are trying to save a file in those software, you need to save it in proper data exchange format. Say for example, IGS or something, then those data can be taken into your analysis software. So say for example, I want to do a topology optimization of a brake disc, right? So I have that IGS model of it. So I'll simply right click, I'll select, I'll import geometry, I'll select break disk. So this break disk is already generated in SolidWorks and I've saved it in IGS format. So I'll simply select it as, I'll simply select that file. So that file would be automatically taken into your geometry. Now, after taking into this geometry, the next step is to go for your modeling of the geometry. So I'll right click it. I'll click on edit. So again, it starts your, it shows that it is starting this mechanical module. So within few minutes, again, you'll be able to see that. So, and one more thing which you need to remember is that whenever you are trying to import a geometry into this ANSYS software, there might be certain amount of data loss. So certain regions where you have the thickness, that thickness you will not be able to see once you import it into software. So you should be very careful while converting into a suitable file format. So this is the disk I've created using SolidWorks. So I've converted into IGS and imported into this software. So if you can see it, I haven't modeled using your design modeler. I have directly imported my model in this software. You can also model it in this ANSYS workbench, but it is a bit complicated. So instead of that, you can go for that software, the CAD software, model it, then again import it into this software. That you can do it. So now your geometry is correct. Your material, by default, I have given the material, and simply select the mesh. You can right click it. You can go for generate mesh. So I'm going for a default mesh. So if I go for a default mesh, don't think that I'll get an exact solution. If you increase the sizing again, as the number of elements increases, your solution will also converge it properly. So this I have given a random mesh. So I'm not particularly focusing on the mesh over here, because if I increase the mesh, you'll be able to get a fine model of this, but the time taken to compute this given problem will also take some time. So since we have seen the stiffness matrix over there, the characteristic equation, so for each element it tries to generate a stiffness matrix. So solving that bigger stiffness matrix would take certain amount of time. So for that reason, I've given it as a default mesh. So after giving a default mesh, now I'll try to apply the boundary conditions. I'll try to apply the loading conditions. So I'll right click on it. I'll go for insert. I'll select fixed support. So I'm trying to fix the given geometry at certain locations. So I'll try to fix this portion. So this, so if you can see it here, you have a face area. So if I simply click on edge, only edge can be selected. So that to the edge of the element. If I want to select the entire face, I need to make it to face. Then only I have an option to select each and every face. So hold your control button in your keyboard, select this face, select the other face. Okay. So you can see something in green color, right? That indicates you are trying to fix that given geometry. Now zoom out. My focus is to fix the geometry over here also. So again, I'll go for zoom model. I'll right click, select the region of my interest. I'll zoom it. I'll select face, select these two areas. Now I'll repeat the same steps number of times so that all the regions would be fixed. So select that box model, select these two faces using the control button, zoom out, select the box zoom, select the region of interest, select these two things. Okay. and even this region has to be fixed. So I'll zoom it. I'll select these two things. So I'll simply click on apply. Now I have defined my fixed support, and along with that fixed support, you know that for a brake disc, you have a brake pads which would apply certain amount of pressure onto the either side of your disc. So what I'll try to do is that on this given region, I'll try to apply certain amount of pressure onto the either side of the disc. So in order to apply that pressure on the either side of the disc, so I'll select static structural. I'll go for insert. So if you go for insert, as I said, along with force, you have one thing called pressure. So I'll select this pressure. So it is asking you to select the geometry where you want to apply the pressure. So I'll select the face, right? I'll select the region of my interest where I want to apply the pressure. I'll select it. Say for example, if you have by mistakenly select that pressure on the wrong side of your geometry, you can simply right click and you can simply delete. So if you want to apply again right click, insert, pressure. Since face is already selected, I'll select this face, click on apply. Now look into the direction, right? I need to apply the pressure along this direction. If I want to apply the pressure onto the other side, if you can simply change the sign, the pressure would be applied onto the opposite side. So the magnitude of pressure, I'm simply giving it as some 0.5 pascals. So I'm applying some 0.5 value onto one side of my disc, and onto the other side, again the brake pad will come into contact with this disc. Again onto this side also, I'll try to give some pressure. So right click, insert, pressure. I'll select this face of interest, again apply, magnitude of pressure. So I'm giving it as some 0.5. So these are the two magnitude of pressures which I have given to the given system. Along with this magnitude, since the disc is subjected to certain amount of rotation, I'll randomly give some rotational velocity to the disc. So again right click, go for insert, select the rotational velocity. So it is asking you to give the magnitude of that rotational velocity. I'm giving it as some 80 radians per second. And again, axis, along which axis you want to apply that. So in order to do that, what I'll do is I'll try to select this face, select this, click on apply. So you can see that I have given a rotational velocity, and that magnitude I have given randomly as some 80 radians per second. Along with that, I have given a fixed support. Along with that, I have applied the pressure onto the either side of the disc. Now simply go for solution, right click, insert. My interest is to find out the deformation, total deformation, and again right click, insert, stress. I want to find out my von Mises stress, so I'll select my von Mises stress. So these are the two output parameters which I want to see. So I'll simply right click on it and I'll click on solve. So it will try to create a mathematical model. As I said, on the background, it uses Python scripting. It tries to generate your stiffness matrix equation. Accordingly, it will try to generate your result. So if you go for deformation, so see, if I click on deformation, your deformation is negligible. What is it? 0.0018251. But if you look into this shape, you might think that my disc has deformed into this shape, but it is not correct. So it is a scaled figure. If I click on this, if I click on to scale, you can see the actual shape of your disc. So you can do it anyway. So for example, if I keep it as 9.4 into auto scale, something like that, it will show that the disc is deformed into this shape. but don't think that it will not deform into this shape. You need to keep always into the true scale so that you can see the actual amount of deformation. You can also animate this. You can simply click on play. You can see this. Since I'm trying to give a simple static structural analysis, it will show you what is the deformation. And along with that, you can, if you click on stress, you can see the value of stress over here. So in this way, you can generate deformation and stress. So after generating the deformation and stress values over here, you can come to the bottom, and here you can see one thing called topology optimization. So let me find it. Yeah, here you can see it, topology optimization. So in order to incorporate this topology optimization, so what I'll try to do is that in which phase I have created my solution. So after solution, I need to continue my topology optimization. So simply I'll select this topology optimization. I'll drop it in solution. So what I have done, I have used my left click of the mouse button, just simply selected the topology optimization and dropped it in solution. So now you can see that you can interlink different types of analysis like this. Now again, I'll go for setup. I'll click on edit. So I'll come back to my given design modeler. So first, since it has a thunderbolt shape like this, so first I'll try to solve this. So I'll first solve the given problem. So it has solved my problem. Now I need to do the topology optimization. So there are different types of topology optimization. So here I'm trying to do a topology optimization based on density. So what I'm trying to do, wherever the stress is acting, there I'm trying to keep the material as is, or if you want it in the later stage, you can add the material. Wherever much amount of stress is not acting, there, why to have that material? Because as I said, you're indirectly increasing the weight of your disc, so which is not good for your automobile applications. So what I'll try to do is that I'll go for density based optimization. So I'll go for response constraint here. So I'm trying to keep percentage to retain as 90. So what does this percentage to retain as 90 indicate? So I'm asking it to keep 90% of mass of the disk as is and just remove 10% of mass where my stress is not acting. So at that region where stress is not acting, there certain amount by default the software will solve and show to you where you need to remove the material. So we'll see it. I'll simply click on solve. So it will try to prepare for optimization. So your solution is done. So whenever I go for topology density, did you find any change from the earlier figure and this figure? So if you look into the earlier disk, you can see that this is the shape. So where the pressure is acting, so there nothing got disturbed. So if you go for optimized region, you can see that the design region is this. So this is the region of interest where I want to remove some material in order to reduce the mass of the given disk. So wherever the pressure is acting, I'm not trying to change any region. So it is excluded. And wherever I have the design region, so at that design region, so I'm trying to remove certain amount of material such that keeping the stress as it is, keeping the deformation as it is, I'm trying to reduce the weight of your disk. So if you go for topology density, you can see certain amount of material at this region got removed. It indicates that whenever you're trying to design a disk of this type, initially this is the shape of the disk. So if you can slightly remove the material on this regions, right, then the mass would be optimized such that you would be able to get the exact stress value and the deformation value. So don't think that whatever the shape it is trying to show, the same shape or the same way I need to again redesign the disk. So what they'll do is that basically they'll again import this given disk into the software, like your design modeler. There they'll try to extract these faces, then try to generate a curvature for this given figure, and again optimize this disk. So this is what will happen whenever you go for a topology optimization. So wherever you want to remove or if you want to reduce the mass of the given thing, you can do this topology optimization and you can see the final output. So the region over here, you need to remove the material, and again after removing the material, make certain operations in the software like fillet or generate a curve using the sketch geometry. You would be able to generate, or you can optimize your mask. So this is nothing but a basic topology optimization. So what I have done is that I've basically introduced you to the concept of basic static structural analysis, how to do it, and along with that I've shown you taking a simple example of a beam, so how design of experiments can be done, and along with those things I've also shown you how to do the topology optimization that is based on your density. So this density and all these values are already there in your material library. If you want to give certain amount of other density values, again, as I said, you need to go to your engineering data. There you can redefine your own material type, give the Young's modulus, give the Poisson's ratio, give the density and all those things, and solve the problem. You'd be able to get the result. So different kind of things can be done. So you can see it here. I have done the static structural analysis. For that I have linked topology optimization. In the similar way, if I want to do some modal analysis, I'll select modal analysis. So say for example, for the disk itself, not particularly for the disk you will do the modal analysis, but I'm trying to show you as an example. So instead of again opening the geometry, again opening the model and doing all those steps, you can simply interlink both the things. So if I go for model, so that model can be directly interlinked to your other analysis. And say for example, you have taken topology optimization. So say for example, we have done the topology optimization for a beam. Now we need to do some random vibration, or if you want to do some transient response analysis or a transient structural analysis. So double click this. So where you want to interlink, I want to interlink this model, right? Or else I'll try to take the same model from here, right? I'll transfer it to transient structural analysis. So these kind of multiple things can also be done using the software analysis. So there are a lot of things which are there to explore. The only thing is that you need to spend some time, understand the basic concept of finite element methods, then use the same techniques, understand what is the procedure you need to follow while doing the analysis, solve it, and get the result. So these are the basic things which you need to do in this finite element methods. As I said earlier, meshing plays an important role. So again, there are certain amount of softwares. If you go to HyperMesh, so HyperMesh has a capability of meshing the given geometry. Along with that, recently they have added analysis to that. So there you can go for different types of meshing. Either you can go for tetrahedral mesh, or you can go for any other different types of meshing. So once you already generate a figure or generate a result over here, you can simply go for display, right? You can keep it in different views, or you can capture this result also. So if you go for solution information, right, it will show the entire thing. So what kind of solution you have done, in where it has converged, and what kind of constraints you have given. If you go for solution information, it will show the entire details. So what kind of analysis is done, how many sub-steps it has taken. You can see it. So if you can look into this element, so you might be wondering what kind of element type it has selected while solving this analysis. So I have shown you earlier in my PPT. So wherever, let me show you that. So since you have a solid, right, the element type which you have is solid 187 or 186. So here, if you go for workbench, and you can see it in solution information, the type of element type which has taken, here it has taken as solid 187. So if you go for ANSYS workbench, so the element type would be taken by default by the software. So if you want to rechange this element type, what you need to do is that you need to write down a code manually. So in order to write down the code, again, you have insert. So here you can see one thing called commands. So we have commands based on mechanical APDL. So APDL is nothing but advanced parametric design language. So in that APDL, you need to write down the manual codes and all. You can change the element type accordingly, solve it, and get the result. So even these things can be done. If you go for ANSYS mechanical, the mechanical APDL software, there for each and everything you need to define your element type. Say for example, if you want to solve a beam problem, you need to define the element type manually. If you are trying to do a solid problem, you need to define an element type manually. So all these things can be done by using this software called ANSYS. So I hope I have given you the basic idea of how to solve a simple static structural analysis, and also how to do the design of experiments, and also how to do the topology optimization. So if anyone has any kind of a doubts, so they can unmute themselves and ask me. So
Are you able to hear me, sir?
Yes, sir.
Is there any possibility for having modeling a particulate composite?
Yes, sir. We have an ANSYS composite module. I'll just show it.
No. Laminate it is possible. Particulate.
Yes, sir. The particulate, if you want to do it, so first you need to determine the material properties. So since you know that I have shown you earlier here, let me show that 1 minute. So if I go for engineering data here, so I can define a new material. So whenever I want to define a new material, say you said that it is a particulate composite, I'll write it as particulate composite. So whenever I go for particulate composite, first I need to know, since it is a composite material, it has 9 elastic constants. It has 3 Young's modulus, 3 Poisson's ratio, and 3 shear modulus. So it indirectly comes under orthotropic elasticity. So here you need to first determine these things manually. So what is the Young's modulus along x direction, y direction, and z, corresponding Poisson's ratio and shear modulus. So if you can do it, you can incorporate the same thing to your model and you can solve it.
You mean that we have to homogenize first, after homogenization, those properties should be obtained, and that way we have to feed it.
Yeah, yes, sir, sure. Yeah. You need to first initially, I guess you have one thing
Because
called
they have
rule of
matrix
mixture.
as well as reinforcement, na?
Yeah, you have rule of mixtures. So
Yeah, yeah.
taking that rule of mixtures, then again, correspondingly, you need to find out the modulus along x, y, z directions. Taking that, you can incorporate into this. So this 9 elastic constants, if you can find it, you can applicable. It is applicable for the same thing. You can incorporate the same thing in the software. You can do the analysis.
Is it possible to have the representative volume element, something like that? Is such facility is there with
So
ANSYS?
it is there in ANSYS composite module, sir. But my field of work, which I basically work, is on additive manufacturing. So I'm not particularly into that module.
Acha.
So I don't know much about that. But I hear that there is one option to give it in ANSYS composite module, your
ANSYS
representative volume function.
Okay, okay.
So if you can explore that composite module a bit more, you'd be able to get certain idea.
Thank you, thank you.
So any other doubts for anyone? So if you have any doubts or anything, please let me know. I'll try to clarify.
Sir, I have a doubt.
Yeah.
Sir, what is the minimum, system requirement for you to run ANSYS in a smooth manner?
See, it all depends upon the type of, if you take a basic example, even 4 GB RAM is sufficient in order to solve any problem in ANSYS. But it all depends upon your number of, elements which you want to define. Say, for example, if you have made a fine mess, right? If you want to solve it in your system, which is having a 4 GB RAM, it would take certain time. So if you have more amount of RAM, say for example 8 GB, it will solve in, say for example 10 minutes. Since you have 4 GB, it will solve in around 25 and 30 minutes. So minimum requirement is 4 GB. So that is more than sufficient. And if you have a graphic card or something, it is more than sufficient. It can run any kind of a problem, not a problem.
Okay, sir, understood. Thank you.
Sir, what are the failure criteria that can be checked for?
Sir, we have different failure criteria. You have hash-in failure criteria. If you go for a composite, you can incorporate that failure criteria. So let me show you that again. So if I go for engineering data on this side, so if you come to this bottom, so you can see the failure criteria and also the damage. So the damage initiation criteria, if you want to incorporate, you can see different types of damage criteria. You have, for a composites, you have PUC criteria. For a composite, again, you have hash-in failure criteria. So all these things can be incorporated. So for these things, you need to incorporate damage modeling again. So that is a different concept which you need to learn. So these things can be done. You can take this tensile fiber failure mode, compressive fiber failure mode, anything. So if you have proper details with you, you can incorporate it. And what is the tensile fiber stiffness reduction? Whether if you want to reduce your stiffness to 50% or 60%. So all these computations can be done over here. So we can incorporate all those things. Those things are available.
Sir, regarding the material property details, so that will be coming directly along with the software, or we should have a separate.
Sir, inbuilt we have certain amount of properties. So if I show engineering data sources, if I show composite materials, so we have certain amount of properties for composite materials, but all the time we will not be using these things. So we need to define properties manually.
So you mean that we have to give the stress strain data graphically, it will take itself?
So sir, if you can see over here, so if I go for composite, we have a composite fiber unidirectional composite properties where we have P preg, tau preg or wet, any kind of thing. These properties are by default available, but for your analysis purpose, this will not serve the purpose. So for your analysis purpose, if you want to evaluate the properties, again you need to calculate you need to go for tensile testing. So create a samples, composite samples according to the ASTM standards, do the tensile testing. From the tensile testing, you can generate the results. You would be able to apply those things, generate the inks modulus, all those things, and same thing can be incorporated into the software. So using this again, you can do it.
Sir, where we have to input, sir, such a type of data? Suppose I have that stress strain data I have generated. So
Okay.
where I have to input such type of data? How can I import that data?
So stress strain data, what is your primary interest? Like, what do you want to find out from the
Sir,
stress strain data?
I have a new composite, say
Okay.
a composite with some filler material, I mean a reinforcement.
Okay.
So I made a tensile test and evaluated some of the properties.
Okay.
So I have with me the stress strain relationship, say with stress in one direction, rather, or say one or two directions, say possibly.
Okay.
So that data I'll have to input into the simulation. So by which I can check it, say this by this finite element process also.
Yeah. Even stress strain data can also be incorporated in this. So one option is that what are the stress strain data you are supposed to get, right? Go to the Excel software. So from that, try to generate the area under the stress strain curve. So that generates your Young's modulus. That is one option. So from that, you can evolve the Young's modulus and incorporate the same thing in the software. If you do it, if you want to do it manually, I guess somewhere here. So not here. Whenever you are trying to do the analysis, there we have an option called stress strain data. So there we can incorporate it. So currently, I guess I need to check it where it is actually. So you can incorporate, sir. It is possible.
Okay, I'll check it, sir. Thank you.
Or else you can do one thing. Some of the softwares, like if you go for a Zwick testing machine, that it directly show you the Young's modulus. Or else if you can go for incorporating the stress strain data in Excel software, generate a stress strain curve. From that, you can generate the area under the stress strain curve, which indirectly gives you the Young's modulus. That is the option you can do it.
Thank you.
Let me. So it is given how long it will take for a beginner to understand the tools and all the practical applications of ANSYS. See, this ANSYS is basic software. So before you go for a software, it's better to understand the mathematics behind this finite element analysis. So as I said, you have one thing called finite element method. See, understanding is very easy. We have lots of tutorials and all. So it's just like if you know the sequence of step, how to solve a problem, you can directly do it in ANSYS. But what is the mathematics which is exactly happening on the background of ANSYS that you need to understand? So if you are a beginner, if you sit on the system, if you practice it for 2 or 3 times continuously, it is very easy to understand. But what is the logic which is happening at the background of ANSYS that you need to understand? If you go for static structural, which I have just shown you, there are simple steps which you need to follow. So if you go for a step-by-step process, you can easily solve the problem. That is not a big issue.
No, sir.
Thank you, Vijay, and I would like to thank the coordinators and the head of the department for giving me this opportunity. I hope my lecture would serve at least has given you certain amount of knowledge on static structural analysis or design of experiments and topology optimization. At least you would have benefited with my lecture. And thank you. Thanks a lot. Okay, sir. Thank you.
Do you have any feedback for today?